So in the last video, what we were looking at was that basically if you have current carrying conductors adjacent to each other, so if you have parallel current carrying conductors carrying current in either opposite or in the same directions, they'll exert forces on each other. And one of the reasons for that, as I talked about, and I'll write this down today, is basically because both of their magnetic fields interact, producing a force. In general, any current carrying conductor in a magnetic field would experience a force. And the reason for that I'm writing now. So if you're ever asked to describe, for example, what we looked at in the last video as well, that why are the two conductors exerting forces on one another, or what we'll see now, one way to describe it is that the magnetic field of the conductor, in that case the magnetic field of each of the wires, because both of those had currents flowing through them, there would be magnetic fields associated with each of them. They would interact to produce forces, right? We'll also see this now, and for that purpose, let me pull up a diagram here. So here are placed two magnets. So there's the north pole of one magnet, south pole of another magnet, and through this there's the current carrying conductor. And it might not be very obvious, but let me make it more obvious that it's taking current in this direction through the through this region of this magnetic field. So I know that there's going to be magnetic fields associated with the magnets as well as with the current. If I were to draw the magnetic fields associated with the magnets themselves, I know that those would look like these. So parallel lines between the faces of the magnet. And now I also know that because of the right hand grip rule, I can figure out what the magnetic field associated with this would be like. All I need to do is point the thumb of my right hand in the direction of this, and I would just need to curl my fingers. And I want all of you to do this with me. So what I would find is that my other four fingers are basically curling in a clockwise direction. So that would give rise to a field that looks like this. Right? So this is how my fingers are curling, and this is the field. Now I've drawn it outside just to make the diagram, just to keep it neat. But basically there would be this field in this entire way. I've just drawn it outside, but it's going to be everywhere in the middle here as well. Now what's going to happen is that the field of the conductor and the field of the magnets are going to interfere, they're going to interact, and this is going to produce a force on this wire. By Newton's third law, by the way, this is a somewhat advanced conversation. Just as there is a force exerted on the wire, there's also force exerted on the magnets, but we don't really talk about it that much because the magnets are obviously much heavier than just this solitary piece of wire. So this force is the more observable one. And let's say if I'm looking into this arrangement from a view like this. So let's add some pretty eyelashes. So if I'm looking at this from here, how would the field lines look like if I could actually see them? All right, let's now have a look at that diagram. So with these as my poles, and then I'm going to make the symbol for this current which is going into the page. If you remember, that's a cross. So that's what this looks like, right? And we know that for this current going into the page, we just use the right hand grip rule. So we know that our fingers would curl around in this direction. We already know how to make the field lines for such a conductor. I'll just draw them for a while and then I'll erase them. So we know that the field lines would basically be lines like these. Circular lines which are increasing in spacing progressively. The third one is going to be even further spaced out like this. And I know that those would be in this way, right? And I also know that additionally I would also have the field lines here associated with this field of itself, which are going to be like these. So let me pick out a shape for that. Yeah. So these are how these field lines are going to be. All right, through the middle as well. I'll have to redraw this anyway. So these are how these field lines would be. So we can see that at some regions, so if I draw these again, just the directions on the bottom parts of the arrows. So in some parts, these fields would be cancelling out because this is to the right, this is to the left. So there would be cancellation happening in this place, and there would be addition happening in this place because both of these are towards the right. So the magnetic field strength would reinforce in these directions. It would cancel out in these directions. That would give me a field pattern that looks something like this. So if I'm redrawing this right now, so the field lines adding up above this region of the conductor and cancelling out below. So the idea is this, that whenever such a force acts on a current carrying conductor, what you should remember is this, that the conductor moves from stronger to weaker field strength regions. Right, so here you can see that the spacing is obviously very less, so the magnetic field strength is a lot here. Here most of the field lines have cancelled out, so here the field strength is weaker. So the force that would be applied on this conductor would be in this direction. Again, you can still use the same idea if you think of the field lines as elastic bands which are stretched. When you let go of these, this conductor is going to go down. Something which is worth remembering regarding the rule that will follow is this, that the force is mutually perpendicular to the current in the field. Now what does mutually perpendicular mean here? Now what mutually perpendicular means here is that, for example, if I talk about the directions of each of these, so the force is downwards, the field lines, and again when I'm talking about the field, I'm talking about the field of the magnet, that's left to right, and the current is into the page, right? So all of these are three dimensions, these are three different directions. One is left, right, the other one is downward, so these are obviously perpendicular to one another, and the third one is into the plane of the screen you're watching this on, so that's also perpendicular, right? So the force is mutually perpendicular to the field and to the current. In such a case where you have the current direction given, the magnetic poles and hence the magnetic field lines shown, you can figure out the direction of the force on the conductor using what's called Fleming's left-hand rule. So Fleming's left-hand rule, I'll be abbreviating this as FLHR just to make writing this easier. As the name says, you have to use your left hand for this, and you'll be working with your first three fingers starting with the thumb. So how the Fleming's left-hand rule works is this, that first of all, why do you use this? And some people do confuse this with Fleming's right-hand rule, which is also going to come up later. This is basically used to find the direction of the force given the current and the magnetic field. Alright, so if you have to find the direction of the force given the current and the field, that's when you use the Fleming's left-hand rule. This is also called the motor effect because this is basically what is used in the DC motor as well. So what you do is, and I want all of you guys to do this with me, is that you position your left hand as shown. And again, as we talked about this, basically your thumb, your index finger and your middle finger are also mutually perpendicular because this angle is also 90, this angle is also 90, and this angle is also 90. Right, so they're mutually perpendicular to one another. Now what you do is with your index finger pointing in the direction of the field, so north to south, this is how the field lines go. Your second or your middle finger pointing from positive to negative because that's how conventional current flows. Then the direction of the thumb is going to give you the direction of the force on the conductor. That's how Fleming's left-hand rule works. And you can also use this with this case. Fleming's left-hand rule is actually what we'll be using instead of making the field lines, which is often tedious, we'll just be using this. So for example, in this case, how this would be used is that my index finger should point north to south. Now, once you figured this out, then for example, and again, it's a bit difficult to show you this, but if my finger is pointing like this, then I know that my finger cannot point, my index finger cannot point in any other direction, right? Then all that can happen is that my finger can rotate about my wrist, and that's about it. But it still has to point from left to right. Now with this, I know that there could only be two possible configurations according to the current, because the current could either be into the page or out of the page. This is for current into the page. So now my my hand is going to rotate such that my middle finger is going into the screen, into the plane of the page that I'm working with, and my thumb now points downwards. So the force on this conductor is downwards. So this is how you use Fleming's left hand rule in action. Now with the Fleming's left hand rule, this just gives us the direction of the force. We don't have a lot of math involved related to the force, but we do need to know the factors which affect the magnitude of the force. So factors affecting the force on such a conductor which is placed in a magnetic field. There are really just three. So the first one is the magnetic field strength. So how strong of magnets we have. The second one is the current. And the third one is the length of the conductor. So length of the conductor in the field. So the idea is that if I increase any of these, the force would increase. And you can, even though you don't really need to know this, but if you want to know why this is so, you just have to remember that the force basically, the force came about because of the interaction of the magnetic field strength of the magnets and that of the current. So if your magnets are stronger, so the magnetic field strength is greater, so that interaction would now create a greater force. Similarly, if your current is greater, so now the magnetic field strength, which basically came about due to the flow of the current, that's also greater, and again that would also lead to a greater force. And as well, if you have a greater length of conductor in the field, so this would also create more magnetic field strength, and again that interaction would also lead to a greater force. So this is basically the idea of how the forces come about. In the videos to follow, we'll be looking at the applications of Fleming's left hand rule and of this idea, which is also called the motor effect, in more detail. So keep watching.